Hello, today I am going to prove the lemma that I have stated in the last presentation, namely that the Poisson probabilities serve as an approximation to the binomial probabilities under the condition that n is large, p is small, and how small is p, so that n into p is close to some positive constant lambda. The key to this proof is to look at this expression as follows. Now let us see how I am getting this expression. You know nck meaning n factorial divided by k factorial and n into n minus k factorial, or you can look at this nck as a ratio n into n minus 1 into n minus 2 up to n minus k plus 1 divided by k factorial. So that k factorial is there. Now how many terms are there in the numerator? N minus 1 all the way up to n minus k plus 1. There are n terms. So from each of those terms I have collected the n, and in that process I get n to the power k. That I have combined with p to the power k. So that is n into p to the power k, and n minus 1 would become 1 minus 1 by n, and similarly the last term n minus k plus 1 would become this term, and 1 minus p to the power n minus k would be, I am keeping it unchanged. Now under the stated condition, that is when np goes to lambda, so the first expression would converge to lambda. So I would now use an equation editor here. Under the stated condition, as so this is the stated condition. If you recall, I am writing it down here. So the first term can you tell me where will this go? The numerator. This would converge to so each of these terms would converge to 1, and this would converge to lambda raised to the power ka. I hope you know the logic, that if xn goes to x and g is a continuous function, then gxn goes to gx. So this would be raised to the power k. So I'll write it like this. Wait, k, and this is lambda. Okay. So I am doing it exactly in the same way I would do on the blackboard, but since here I am to use the equation editor, so the space is a bit slow. But then this is as good as it gets. So the numerator, we have found out, it goes to lambda to the power k. The denominator is a constant k factorial, so we need not worry. Now here, now what happens to this expression? Again, you see there are two terms here. One term is so I can write this as 1 minus, so I can write this equal to, I hope you can see this, but let me still do everything. This is equal to what? This is 1 minus raised to the power, here it would be only n, and then in the denominator this would be paste 1 minus this is simple, right, raised to the power k. Now k is a constant, so as p goes to 0, the denominator goes to 0. But what about the numerator? See, p is now a function of n. And how is it? It is equivalent to, so I will use this symbol. I don't know whether it is there in the equation editor. Let me check. Yes, it is there. Okay. So this is equivalent to, equivalent means if you take the ratio and let n tends to infinity, p tends to 0, then the ratio goes to 1. So this is equivalent to 1 minus lambda by n. Why? Because np goes to lambda. So p is going to 0 in the same way as lambda by n would go to 0. Okay, my goodness. Now raised to the power n. This expression raised to the power n. Now, where does this go? Now, you know that from your 10 plus 2 level calculus, that this converges to where? E to the power minus lambda, and hence the result. So when you so we can let us align it, so that align it, and so this completes the proof. So you see in ck, so the first ratio would converge to lambda k by k factorial, and the second expression goes to e to the power minus lambda. So this completes the proof. So therefore this would go to e to the power minus lambda, lambda to the power k by k factorial. And so here now, so the proof is complete. Remarks. So Poisson distribution serves as the probability model of number of successes, successes, number of successes in a large number of Bernoulli trials, where the chance of success in each outcome is small. So the word Bernoulli trial refers to any random experiment that has two possible outcomes. I repeated, I had said that a random experiment has two properties, that it has more than one possible outcomes and you can assign probabilities to the outcomes of that experiment, and second is that the experiment can be repeated. So a Bernoulli trial is a random experiment with two outcomes. So suppose you repeat a Bernoulli trial a large number of times, that is a classical example of a Bernoulli trial. So you toss a coin a large number of times, where the chance of getting head, let us say, is very small. It is a biased coin. So then n would then the number of heads or the number of successes, that would follow binomial NP. But for large n and small p, we have learned that this probability distribution is close to the formula e to the power minus lambda, lambda to the power k by k factorial. Now, a practical application is this. Let x denote the equal to this, so we don't need to write denote number of spelling mistakes in a published book. So I have said published book, that means that has gone through the rigorous peer reviewing and publishing process. So it is like it is very less likely to contain spelling mistake. So there may be one or two spelling mistake, but the chance that a particular word is spelled wrong in a published book is very small. So here P is the chance that a particular word is wrongly spelled. So each word is either correct or wrong. Now in any book or any large monograph, there are going to be thousands of words, right? Each page is going to contain hundreds of words, and you have hundreds of pages. So total number of words, that would be your n, and the chance that each word is correct or not, so that is Bernoulli. P denotes the supposed chance that it is mistake, because you are counting the number of mistakes. So here this is a classical example of this scenario where you are counting the number of mistakes where the chance of each mistake is small. So this distribution can be represented very well by Poisson distribution. Now you may be confused that in the Poisson probability I am writing k equal to 0 or y equal to 0, 1, 2, dot, dot, infinity. But in practice, you see, when you are approximating binomial distribution by Poisson, this k is always going to be 0, 1, 2 up to n. But the point is, n tends to infinity means n is very large. In practice, there is nothing called infinity. It only represents a very large number. It's a symbol. So now I will go to another distribution, namely the geometric distribution. Geometric distribution. This is also an example of a discrete random variable. A discrete random variable with infinitely many values. A discrete random variable, discrete random variable taking values 0, 1 to same as the Poissons, and the geometric values are same, probabilities are different. Taking, no need for a bold, taking, let me write non-negative integer values, that is i.e. mean non-negative integer valued random variable is said to follow geometric P distribution if probability x equal to k, this is given by the formula, insert equation again. So it is similar to writing in the blackboard, but of course this process gets very slow, especially